In this video, we're going to talk about relative solubility and what we can and cannot compare when we are looking at different compounds and at their solubility products or their molar solubility. So molar solubility is used to calculate solubility product, and they're related, but you can't directly compare solubility products and infer something about molar solubility always. Now, this works fine if the products are going to be the same number of ions. So here I have an example where silver iodide and copper iodide and calcium sulfate all have 2 ions as products. We have calcium +2 and sulfate ion -2. Copper +1 and iodine -1, and silver +1 and iodine -1. And so for each of these compounds here, we'll have 2 ions as products, which means that the coefficients in front of those products, when we balance the equation, will be the same. And that's why we can directly compare the molar solubility product and infer something about the solubility of each of these compared to one another. And so from our solubility product information, we can see that copper sulfate has the largest solubility product. It has the least negative exponent over the 10. And so the most of these 3, calcium sulfate will dissolve the most in water, whereas silver iodide with 1.5 times 10 to the -6, that'll actually be our least soluble compound of these 3. And we are just directly comparing the solubility products because we have the same coefficients in our balanced reaction for all 3 of these. But if we do not produce the same ions when we want to compare different compound solubility, we can't use the solubility product to do a direct comparison. Instead, we're going to need to calculate the molar solubility and compare that. So when we have the different number of ions, we're going to need to compare solubility product or molar solubility. It's easy to get these names confused. So let's walk through an example of this to show you what I mean. So I have 3 different salts, and they have different solubility products listed that we looked up in a table of published results. So the question is, which one is the most soluble? Well, I cannot tell you based on the solubility products which one that is. If I did, I would probably say that copper sulfide is the most soluble of these. So I'm going to need to compare the molar solubility instead. So I need to calculate that for each of these. I'm going to put our equation that we're using for this back up. Where did I put it? There we go. So our molar solubility is going to be equal to the root that is m, or the coefficients, n plus m. And then we'll have our Ks, our solubility product, KSP, divided by our coefficients to their own exponent multiplied together. So for copper sulfide, when this reacts with water, it will, or is dissolved in water, it'll produce a copper ion and a sulfide ion. And so we'll have coefficients that equal 1 and 1. And that's our N and our M in our equation. So if I go ahead and calculate that for copper sulfide, this is what we'll get. Our solubility product will be equal to 1 plus 1. So that's going to be 2. Our KSP is 8.5 times 10 to the -45. And width, it'll be 1 to the power of 1 times 1 to the power of 1, or it'll be 1. When I plug this into my calculator, I'm then really taking the square root. That 1 plus 1 is 2, so I'm looking at the square root of 8.5 times 10 to the -45th divided by 1. And I get a value that is 9.22 times 10 to the -23rd molar. So that's the solubility product for copper sulfide. Or sorry, that is the molar solubility for copper sulfide. Now I'm going to do the same process for my other two. With my silver sulfide, when this is added to water, some of it will dissolve, and instead of producing 2 ions, it's going to produce 3. I have 2 silver ions that'll form and 1 sulfide ion. So that's going to change my N and M values. Now my N is going to be equal to 2 and my M is going to be equal to 1. So that'll change my overall equation here. So for silver sulfide, solubility will be equal to 2 plus 1, which will be 3. So this will be the cube root. My solubility product is 1.6 times 10 to the negative 49, and this will be divided by 2 squared times 1 to the first. So I'll have the cube root, 1.6 times 10 to the negative 49, divided by 4. When I plug this into my calculator, I get a value that is 3.42 times 10 to the negative 17th molar. So I can see that my silver sulfide is actually more soluble, see, than my, sorry about the screen there, than my copper sulfide, which isn't something I would have predicted based on the solubility products if I compared them. All right, so let's take this a step further and let's look at bismuth sulfide. So this is going to form, when this is dissolved in water, I'll bring it down here, it'll form 2 bismuth ions and 3 sulfide ions. So I'll have a N equal to 2 and an M equal to 3. So let's set up our equation for bismuth sulfide. Solubility will be equal to, so it's 2 plus 3, and now what's the actual word for the root, the 5th root, maybe? My solubility product is 1.1 times 10 to the negative 73, so very small. I'm going to divide that by 2 squared times 3 cubed. So this is going to look like the 5th root, if I'm saying that correctly. My KSP divided by 4 times 27. Now your calculator probably doesn't have a 5th root. Maybe it does. So this is a good reminder about when you're taking the root of something, it's really like taking a fraction as an exponent. So I can rewrite this in a way that will be easier to plug into my calculator. 4 times 27 is going to be 108. And I'm going to then take this to the power of 1/5. So that's a little easier to plug into the calculator. When I do that, I'm going to get a value that is 1.00 times 10 to the negative 15th molar. So actually I find myself here. My bismuth sulfide is actually the most soluble of these 3 compounds. If I had just directly compared the solubility products, I wouldn't have come to that conclusion at all. So remember, when comparing solubility, you can only use the solubility product to compare if the ions that dissolve are the same molar ratio between your different compounds.